All right, so this part, there's going to be no equations. This is a lot of information, and I'm just going to preface this by saying this is really the edge of my understanding. So if I say I don't know, I really have no clue. So, all right. We're going to pretend that there's 4 fundamental forces in the universe. How about that? Because it's not actually true, but let's pretend there's 4 fundamental forces in the universe, okay? Okay, great. All right, so the one we are most familiar with and the one that's most least understood is gravity. Gravity is the least understood of the forces. It drops off like 1 over r squared. We learned that from the equation. Gravitational force was Gmm over r squared. Drops off like 1 over r squared. But why we don't understand the gravitational interaction is there's no intermediary particle that causes this interaction that we've yet to discover. Some people think there is a particle called a graviton, but we've never observed it. There's a lot of theories about how gravity works, but this is sort of the edge of our understanding. Mm-hmm.
I kind of have a question on that. I was under the impression, apparently a theory, that it was due to the perpetual motion of Earth. Perpetual motion? What? Well, motion, right? Spinning.
Oh, that keeps things in orbit, like the moon?
Well, that keeps gravity to the planet. It's the spinning involved that does that.
No.
Okay. Well, spinning.
No, anything with mass has a gravitational pull. So,
And technically spins.
doesn't have to spin. I'm not spinning.
Yes, you are. You're on the Earth and it's spinning.
Well, I could be in space and standing there, and just by virtue of having mass, I will have a gravitational pull. So it's very, very, very small. So if there's something, if I'm standing in there in space and there's a spaceship and it's just out of reach, my gravitational pull and the pull of that spaceship, it would take a billion years before we were ever gravitationally attracted enough that I could actually get to that spaceship. And I could do this all I wanted, and if it was just one hand length out of reach, I could never get to that spaceship. So it's got nothing to do with spin, but the reason it's weird is because all the other forces that we do understand well have an intermediary particle. So the electromagnetic interaction, electricity and magnetism, has electrons. They have charge. They intrinsically have charge, and electrons are magnetic dipoles. So they're like a little tiny north-south magnet. So that's where we get magnetism, is the electrons. That's where we get electricity and magnetism. So people go, there must be a particle that causes gravity, but we haven't ever figured it out. The electromagnetic interaction is very similar to gravity. We know it drops off like 1 over r squared. The next 2 forces are poorly, they don't come up in introductory physics ever. So we've never learned about them yet. The strong interaction, or the nuclear force, this is what holds the nucleus together. It's about 100 times as strong as the electromagnetic interaction, but it drops off quicker than 1 over r squared. So it's not strong enough that it will pull electrons in. The nucleus and where the electrons are orbiting is extremely far apart. If you think that most of atoms is just empty space, a lot of empty space. So it's far enough away that this doesn't pull the electrons into the nucleus like the Rutherford model predicted. The weak interaction has an even narrower place where it interacts. It's responsible for beta decay, such as the conversion from a neutron into a proton, an electron, and an antineutrino. That's beta decay. If anyone's taken chemistry, you probably did some nuclear reactions, and as radioactive elements decay, they create byproduct byproduct particles. So this is part of that process. This is also responsible for the decay of other unstable particles It's very, very, very weak, weaker than the strong interaction by a factor of 10 to the 9th, and it drops off very, very quickly. So, and one way I've heard this described is this is the force that keeps the protons from crashing into each other inside the nucleus. So there's a strong interaction that holds them together, and the weak interaction keeps them from colliding. Buffer, yeah. And the reason I say let's pretend there are 4 fundamental forces is because very, very recent discoveries in the last few years have found there could possibly be more than 4, maybe up to 7. But when I learned physics, it was 4, and your book says 4, so we'll go with 4.
That was completely wrong.
Well, when things are out of date, I'm not going to blame the book for being out of date. So there's a whole lot of subatomic particles, and this becomes like, you know, I don't know. I wouldn't worry too much about the terminology because you're not going to be tested on this. This is just free information. So we know about electrons, protons, and neutrons. They all have spin 1/2, and photons have spin equal to 1. Positrons I talked about. Well, photons can be created and destroyed singly. So we create photons every time an electron jumps down in energy level. In order to create electrons, you always have to create a positron, so we don't violate conservation of energy. And we already talked about this, so. Positrons do not occur in ordinary matter. They're produced via pair production requiring a minimum energy of 1 mega electron volt. So in order to actually create electrons and positron pairs, you need a really big explosion to have that much energy. And we'll talk about how we can create these explosions. More particles. Antiprotons, they're negatively charged protons, sort of like the positron is for an electron. Neutrinos, there's so many neutrinos I can't keep track. These are cosmic ray particles that react very weakly with matter. They're so small they pass right through the Earth. They pass right through your body. In fact, even to detect them, they have these giant rooms way, 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 way down in the Earth. And they fill the room with water, and then the whole room is filled with detectors on the walls. And the water slows down the neutrinos enough that they hope that one of the detectors on the wall will actually hit that neutrino, or the neutrino will hit the detector. And they can have those things operational for years before they even get one neutrino detected. So they're really small, but there's some of these theories that require understanding neutrinos, so that's why they try and detect them. And then we've got some classifications. Fermions, these are particles that have a half integer spin, so that would be protons, neutrons, and electrons. You could also have one and a half spin, blah. You get all these exotic particles when you get into this. Leptons or fermions that do not have strong interactions and have spin 1/2, so that's electrons and its neutrino, the muon and its neutrino, and the tau particle and its neutrino. Bosons are particles with integer spin, 0, 1, 2. So I said that the photon had an integer spin of 1, so a photon would be a boson. That's not. Or 0. Yeah.
We're not going to get back to that.
Oh God. Let's not go there.
I tried to bring it back up earlier.
Hadrons, these are particles with strong interactions and all have antiparticles. Mesons have spin 0 or 1, making them all bosons. Pi mesons, called pions, blah, blah, blah. Blah, 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 blah. Lots of particles. Baryons, these are particles with half integer spin. And these include nucleons. Nucleons are called nucleons because they're in the nucleus. So that's protons and neutrons. And then there are hyperons. And then there are more. And it goes on and on and on and on.
They all end up on though, right?
No.
And this was all came up with by morons.
Okay, so all of those are a lot of particles. They all have different mass. They all have different de Broglie wavelengths. They all are going to interact differently with forces. So when we create collisions with particles and you create these exotic byproducts, they track where they go, and based on the path that they took or how they interact with other particles when they collide with something else, they can figure out what their mass is, what their velocity is, and how long they exist before they decay into something else. So characterizing all these properties is how they're able to say, yes, it was this kind of particle because we figured out it was going this fast and it had this kind of curvature in the presence of this magnetic field, so it's got this property and this property. So that's how they're able to figure out what particles they're creating when they do these big collisions. So the goal of all modern theoretical physicists is to figure out the theory of everything. What this is they want to get one formula, basically, or one theorem that describes everything in the universe, that describes every fundamental force. But currently they don't have that. We don't even understand gravitational force, so we have to understand gravitational force before we can help reconcile it with the other three forces. So there have been some forces that have been reconciled. So one of them is the weak interaction and the electromagnetic interaction. So this is called the electroweak theory. And so the mass difference between photons, which have zero mass, and weak bosons makes the electromagnetic and weak interactions behave quite differently at low energies. But if you have enough energy on the order of 100 giga-electron volts, then this distinction disappears and the two merge into a single interaction. So the only way they could do that is by creating very big explosions with lots of energy. And actually 10 giga-electron volts nowadays is like nothing. We got the Hadron Collider with 14 TeVs, tera electron volts. All right, so then comes the grand unified theory. You may have heard of GUT. Anybody heard of GUT, grand unified theory? This one is trying to reconcile the strong interaction force with the electroweak interaction. So it's bringing in a third force. So some experiments to try and verify GUT, they're looking at proton decay and they're looking for magnetic monopoles. We said we've never found them in nature, like electrons are a north and south magnet, but you never find just a north side. Like you would with the positive and negative charge, you've got one. You know, electron is negatively charged. It's not a dipole, but they've never found a magnetic monopole. If they did, they'd be able to verify the grand unified theory. And then the theory of everything reconciles all fundamental forces all together. And there's lots of theories. You've probably heard of superstring theory. That's a very popular one.
String theory?
So superstring theory requires multiple dimensions, I think up to 10 dimensions in the universe in order to reconcile the four forces. It's derived completely mathematically. And a very charismatic physicist named Brian Greene has come up with nice stories to tell about what his math would actually mean if we were living in a 10-dimensional universe. I feel like theorists do this. They come up with something that works mathematically, and then the other half of their job is, how do I sell this to the public? I have to come up with a story about why my math makes sense. The math makes sense. What's that?
Dragons Eat Unicorn?
Kinda. I don't know if anybody has read the Brian Greene book. What is it called? Oh, I'm totally blanking on his book. It's very popular.
Starts with the word super.
No.
Hold on.
Brian Greene.
Find my book.
Go by my book. The Elegant Universe?
Yes, The Elegant Universe. I saw his talk. He's got a very pretty PowerPoint, and people go, ooh and ah, he must be telling the truth because it says so on his PowerPoint. Just remember, he made all that shit up, okay? He's got this pretty picture of these rolled up dimensions and ants crawling over them like they're spheres, and people go, oh, that must be reality because he made it into his PowerPoint presentation. It's a theoretical physicist. It's a theory, folks. I don't. Anyway, I'll get off my soapbox. So other theories, there's one called supersymmetry, where every boson and fermion has to have a super partner of the other spin type. I don't understand that one at all, so I'm not even going to try and touch it with a 10-foot pole.
So
Abuse the word super.
They love it, don't they?
interesting is there is a Netflix thing called Particle Fever. I don't know if you saw it. But they're actually talking about when they were looking for the Higgs boson.
Yeah.
And they said, if it's here, it proves I'm right. And the other person's like, yeah, but if it's here, it proves I'm right. And when they came back, it was in between. They said, well, crap, we don't know what the hell that means.
Well, that must be why yeah, there's not been a whole lot of like big hoopla about discovering it because
Came in right in the middle between their
two prevailing theories.
And they're like, well, we're both out of the water. So now we don't know what it means. So it disproved both of them.
Yeah.
Simultaneously.
Nice. I love that.
So now nobody knows. That's cool.
People have theories. People always have theories. You just have to convince enough other people that your theory is right. I think that's how it goes. So to kind of lead our way into the Higgs boson, particle accelerators are used to produce very precise they create precisely controlled beams of particles, whether it's electrons or positrons, protons even, or heavy ions, whatever, with the specific frequency or specific energy. And you can use these collisions, so you can send your beam and collide it into a plate, or you can send the beams and collide them into each other. And the purpose is to create new particles. So if you collide electrons and positrons, you can create photons.
I have a question.
Yeah.
So positrons are up there. Does that mean that when they're running the collider, do they start to get a peak before they actually, like the moment they hit, they actually start to see a peak?
I don't actually know. That's a good question.
Because that would be that backwards time thing, right? It seems like it would give a reading the moment before it's getting hit.
Maybe.
Okay.
I don't know. I haven't read about electron-positron collisions, but it'd be interesting to know what that looks like, since the positrons are traveling backwards in time, or how they even get enough positron. I don't know. I have a lot of questions about that too.
Okay.
It's a good question. No, good question. Again, I don't know much about this area of physics. You have to specialize in this to learn about it. Sadly, that's how it goes. So high energy particles have short de Broglie wavelengths, and so you can use that to probe the interiors of other particles. So we talk about electrons being like a particle, or positron or proton being a particle, but they are divisible. There is something inside them, and there's something called quarks that make up particles. And so if you want to know what makes up the inside of those particles, then you have to probe them with really, really, really small particles to do that. So that's one aspect of particle accelerators. And we can also create nuclear reactions for scientific or medical uses. So the Large Hadron Collider, a lot of people talk about. This is a synchrotron at CERN, which is in Switzerland. It's used to collide two oppositely traveling beams of protons. So they found that if they're just colliding one beam into a plate, you don't get nearly as much energy as if you have two beams that already have energy and you collide those together. The goal when they built it was to get 14 tera-electron volts of energy, and they didn't think they would really be able to do what they needed to do to study the physics they wanted to study unless they could get to that energy benchmark. It's 100 meters underground. The whole radius or the diameter of the rotation of the beams is 8.5 kilometers. So the rotating beams of protons, when they're going around that ring, they'll go around 11,000 times per second. That's
a big ring.
Mind-boggling. So one of the most popular things that people have heard of is trying to detect the Higgs boson. Other things is they're trying to verify the Standard Model, verify supersymmetry, possibly detect particles responsible for dark matter. So there's a lot of cool things that they want to do with it. This is an overhead view. There's the Alps in the background, It's really big. So the Higgs boson, so the problem with the electroweak theory, this is the theory that actually combined the electrostatic force, or electromagnetic force and the weak force together. Photons are massless, but weak bosons, which are one of the first byproducts of particle creation, are really massive. And so to figure out how that happened, that they call it broken symmetry, they said there has to be a boson called the Higgs boson that's giving that particle mass. So it's the intermediary particle that gives all other particles mass. So it's expected, the mass is expected to be less than 1 tera-electron volt per speed of light squared. That's a weird way to measure it. I guess it's probably coming from E equals mc squared. So this is how you can describe the rest energy of any particle, equals mc squared. So the rest mass would be energy over the speed of light squared. So that's where those units are coming from. So in December 2012, they started getting detections, and they're like, the data coming back is showing that we're getting the Higgs. And you can't just get the Higgs once. You've got to get the Higgs thousands of times before you say, yes, we are finding what we think we're supposed to be finding. So they didn't actually announce until February, I think of 2013, that they were pretty sure they were detecting the Higgs boson, but we need to collect more data. That's what they said. And then in 2014, they confirmed, we collected enough data, we are certain we've found the Higgs boson. The guys that discovered it got the Nobel Prize that year. And as of last week, they got the Large Hadron Collider to achieve 13 tera-electron volts. So they say, we're ready. We are ready to start doing the physics that this machine was designed to do. So it's basically been in upgrade mode for the last 2 years and getting itself operational. And they've run tests, and now it's showing that they can create that kind of energy collisions. So now they can do all the other things they're hoping to do. So, questions? I know. I'm not going to be able to answer them. But I put in a lot of links in here if you're interested in following the links and going down the rabbit hole. Maybe something fun to do after finals.
Yeah.
Speaking of final. So our finals is next Wednesday, 5:30 to 8 p.m. Our exam will be held downstairs in room 106. I'll put a note on the door up here, so you, if you come up here, you'll be like, oh, class was canceled. No, it won't. Won't be canceled. You're allowed one sheet of notes. It's largely like the midterm. The exam is comprehensive, but it's very weighted towards the second half of the term. Just like the midterm, you're going to have about 10 multiple choice questions that are conceptual. You've seen them all before. In fact, I put all of the ones post-midterm that we've done in lectures as review concept questions. I've put them on your weekly online activity, so you'll get the practice of revisiting them this week. Another thing that is available to you on the course website, if you've checked out the final exam folder, I believe, someone verify this if I'm lying, that there's a worksheet with all the lenses and all the mirrors and every location where the object could be, and you can draw your rays and all that good stuff. Remember, on the test, I'm not going to be looking for your rays, so you don't have to draw the rays on the test. I'm looking for your answer to those 3 questions. Is it upright or inverted? Is it real or virtual? Is it enlarged or reduced to the same size? So there's what? I think there's 12 possible pictures for you to practice. So that's another thing you can practice that most likely will be on the exam, because it usually is. Anything else to say?
Are you going to update the sheet?
Equation sheet, yes. That's my plan.
Still,
I know. I was going to do that after I finished grading the labs, and I didn't finish grading the labs, so it's on my to-do list for tonight. Yeah. So before we do the exam review, there are concept questions here that cover chapter 39 that we've done today. So you can practice these, but again, they're also on your weekly online activities, so you will see them again. Okay, so midterm, what did we have on the midterm? Generally, I don't repeat topics on the final, so I'm trying to find our midterm so I can remember what was on it. Oh, there it is. If you attached your note sheet to your midterm, it is. Do you want it? I don't want your note sheet. You don't ever have to attach it. I don't think it's on here. Nope, you didn't attach it. You lost it?
No, it's in my big pile at home.
Uh-oh. Okay, so let me see what we covered on the midterm as far as the workout style problems. So we did, okay, simple harmonic motion, so that's one-dimensional waves. And we did two-dimensional waves. Okay, we did fluids, so we did Archimedes and Pascal's. I think we're done with fluids. And we had light refraction. And light refraction with total internal reflection. So, things that I'm not seeing, we didn't do as far as lecture 4 goes. Oh wait, Doppler effect didn't show up. That goes back to the lecture 2.
So that's still a possibility?
So yeah, let's see. So pre-midterm stuff.
Question on there?
The bat question, maybe. It's a good one to study. Depends on if it shows up on one of my sample exams that you guys have available to you. If it shows up on the sample exam, then it's not going to show up on the final.
But there's a Doppler one on the sample.
Is it the bat one? Like where it's a bounce and come back? Double Doppler?
That was it. I don't remember which one it was. I just remember seeing it.
Was it a whale or a dolphin?
I hated that one. Because it's like, do you treat the wall as moving, but the bat's moving? It's like...
You treat the wall as stationary, but you have to change whether it's the source or the detector. So you do Doppler shift twice, and first the wall is the detector, and then the wall is the source. But it always has zero velocity.
It says it's good for storm chasers or after a tornado.
Okay, so it is very possible that if I do Doppler effect that it will be like the bat problem. Yeah. Because that storm chaser one's different, so it's, yeah. And there was something else in lecture 2. Oh, instruments. Did we do, that was velocities of a string, so we didn't do pipes and stuff. Open versus closed pipes. So yeah, instruments, that didn't come up on midterm. And then
I'm really happy it wasn't there.
now you get to revisit it. Hi, Richard. And then, so we didn't, for the light lecture, the first light lecture, we didn't do chromatic dispersion. And a problem like that was where you have white light that comes in, hits a plate of glass or something, and then when it goes through, the red and the blue beams have different angles. So that it's just Snell's law. It's not overly complicated if we did that problem. Yeah, lecture 4.
But I've already forgotten all that stuff.
force for me is like, I don't know which class.
What was lecture 3?
Physics class am I in right now?
What's that?
That was-
Oh, fluids, right. We said we're done with fluids. Good, okay. And then we didn't do polarization by reflection.